All right, ladies and gentlemen, here we go. We're going to get started. We got chapter 5, 6. We're doing logarithmic and exponential equations today. And that's our goal. We're going to solve logarithmic equations using properties of logs and refresh your memory of those. And then we're going to solve some exponentials, a new, different way. Okay. So as I take a look, we had a warm up today, but because we don't have a ton of time, because it's Corona time, we have 5 less minutes and yada, yada. We're going to dive right into this one. Together, just a reminder, if I have the log of m times n, then I should know that is the log of m plus the log of n, and whatever that base is stays the base. Okay, so if it's multiplication, it's addition, and if it's division, then we should know it's subtraction of logs, both base a's. The last one we talked about was the exponent rule. If I have an exponent inside of a log, we can drop it like it's hot in front. So now we have r times log of m base a. Okay, so again, we had the sum, the difference, and now our exponent rule of logs. Well, our last property of logs that I got to show you, and I kind of showed you this in 5.5 stuff, is if I have two logs that are equal, then the stuff inside the logs, m and n, must be equal. Right? That makes sense, right? So if I have two logs equal, then the stuff inside must be equal. Okay, so that's our goal for number one is I see I have logs on either side. What I'm trying to do is get log base 7 equal to log base 7. Well, the problem I have right now is this 3's in the way. Okay, well, from up here, we should know that's an exponent. So we can take that and put it back on top. Okay, so now that represents log of x cubed to the 7th, and that equals log of 625 base 7. And now we have logs equal logs, so now the stuff on the inside must be equal. So we should be able to write x cubed equal to 625 then. Okay. So know why you got rid of the logs. Okay. When we're always trying to get rid of logs one way or another. If we have an equation that involves a log, we got to get rid of it. Well, this is one way, just using our property. If log equal log, then stuff inside is equal. That's one of the rules. Okay. Last but not least, we want to solve for x, and we can just cube root both sides. Now, if they want an exact value or ask you to simplify it, this is where you would want to break it down using your factor trees. So if divide by 5, we get 125. Divide by 5, we get 25. Divide by 5, we get 5 and 5. When it's an index of 3, a cube root, we're looking for 3 of a kind. Okay, so I circle those 5 3's and I write that one time. And then, oh, this guy's left inside of the cube root. He doesn't have 3 of a kind. So my final answer, if it asks for simplified form, would be 5 cube root of 5. Now, if they ask for decimal, I don't have to do any of that work. This is just a refresher on how to do that. I would use the math menu. I'd go all the way down to cube root number 4 and just do 625. And if I round that, that's what, 8.550 approximately. So if they ask for the approximate, rounded to 3 decimal places of 8.550. That 8 rounds the 9 up to 10, which rounds the 4 up to a 5. Okay, so look to see what MathLab wants, exact value versus an approximate value rounded to 3 decimal places. Okay, any questions with that? So this is one of the scenarios that you're going to run into if I have log equal log. Okay, here's another scenario. You might have logs on the same side. Okay, well, if I have logs on the same side, then I want to convert back into one log. We want to condense this. We want to make a single log here. And that's what we learned in the last section. So we want a single log. So if it's log plus a log, we do multiplication. If it's log minus a log, we do division of the two. Okay, so in this case, it's log plus a log. So we're going to multiply. I'm going to take x plus 3. I'm going to multiply it to x minus 3. And put it inside of one log. Okay. Any questions so far? So that's all inside of this log. Well, now I can, if I want to go even further, I can FOIL this thing. And I would probably gone right to this step, but just so we have the notes on it. X times x is x squared. Outers and inners is going to cancel. It's negative 3x and 3x. That's 0x. And then 3 times negative 3 is negative 9. Okay, so we took those two logs and condensed it down to one log. Okay. Well, now I got to get rid of this log. But it's not like this guy. It's not log equal log. It's log equal number. So we have to know why we're getting rid of this log. We can't just use math magic and just make the log disappear. You have to know why it's changing or disappearing. Okay, this one's pretty easy to follow. Log equal log, get rid of the logs. What do you do when it's log equal number? How do you get rid of this log is my question. Does anybody know? And this takes us back to 5.4, chapter 5.4 stuff. What do you do when it's log equal a number? How do you solve that logarithmic equation? Any ideas? How do you get rid of this log? How do we solve for x? Mr. Gotch, why don't you just tell us how to solve it? Is that what you want? Yes, Mr. Gotch, it's Monday. It's our last day of notes. Come on, nobody's got this, huh? You guys remember this? Anytime I get log equal a number, okay, we must convert to exponential. We should know we have a base, we have a number, and we have an exponent. This is my exponent. That's my base. That's the number on the outside. So my base is 4. My exponent equals or equals exponent, that's 2. And now that's equal to x squared minus 9. Okay, so you have to convert to exponential. So I've converted to exponential. All right, so convert to exponential, base exponent equals x squared minus 9. Well, simplify. 4 squared we know is 16. And then how do you guys want to solve this thing? How do you solve this quadratic, y'all? You can at least answer that question. How do we solve for x?
Add the 9 over.
Yeah, add the 9. You could also subtract 16 and do the factor method, or you can add the 9 and do the square root method. It's kind of whatever you want. So add 9, I get 25 equals x squared, and then square root it. And we get x equals plus or minus 5, technically. So technically, there's 2 answers here. Now, because we're dealing with logs, there's restriction in our domain. Okay, so this is a reminder that we need to check it. Anytime we know we have restrictions in domains, you've got to check it. Okay, so if I plug in 5, 5 plus 3 is 8, 5 minus 3 is okay. When I run into issues is if I get log of 0. If I get the log of 0, I get an error message. You cannot do log of 0. Okay, and the reason, if I was just going to graph, log of x, just a basic graph of a logarithmic function. Reminder right here at 0, there's an asymptote there, right? And then there's nothing to the left, nothing that's negative. It's only positive values. So we talked about domain of a log has to be greater than 0. Okay. It can't be 0, can't be negative. If I type in the log of 0, it's undefined. There's an asymptote there. If I do a log of negative, I don't know, 5, no real answer. Okay, so you cannot plug in negative numbers for logs. Can't plug in 0. It's got to be greater than 0. So if I do negative 5 here, negative 5 plus 3 is negative 2. And the log of negative 2, no matter what that base is undefined. Okay, so maybe make note of that. Log of a negative number is UND. It's undefined. Okay, so x equals 5 works, but negative 5 does not work. So the only answer you have there is 5. If I plug in negative 5 plus 3 is negative 2. Log of negative 2, can't do it. Negative 5 minus 3 is negative 8. Log of negative 8, can't do it. It's undefined. Okay, so be very careful when you're plugging these answers into MyMathLab if you're solving logarithmic equations. Technically, they have to be positive logs. Okay, so double check it. All right, ladies and gentlemen, do you have any questions on examples 1 or 2? Solving logarithmic equations. Only answer you should get on number 2 is 5. All right, I don't hear any questions. Are you still awake? Oh boy, I hope so. All right, last but not least, we got properties of exponentials. This is goal number 2, ladies and gentlemen. We'll go through a few examples, and then it'll be time to go. If I take a look, the new property is just the opposite of the old property. Here, if this one says log equal log, then the stuff on the inside is equal. Well, this one says if these two guys are equal, then the logs of these two guys have to be equal. That's our new property, okay? Well, solving exponential equations. Now we have this property and we have the old property. I want to review the old property, the old way, and that was from chapter 5.3 to solve exponentials. And then I'll show you the new way. Okay. Now, technically, this one, we can do either one. But when we get to example 5, we have to know how to do the new way. So we're going to practice on these easier problems here, example 3 and 4. The old way was, well, if I have an exponential, like 2 to the x equals 27, well, all we did was we converted to logarithmic. We did exponent equals log with the same base, and then that number. We said, well, if I want to solve for x in the exponent, I said exponent equals log with the same base. The base of the exponential is 2, and the number all by itself is 27, and we were done. And we got x equals log of 27 base 2. Well, here's the new way. The new way says, if these two are equal, then the logs of these two are equal. Now, you can use any log you want. You can use log logs, common logs, or you can use natural logs, or you can do logs of 5s. You can do logs base 20s. I don't care, but I usually use natural logs. Okay. And the reason why I use natural logs, number 1, it's less writing. Log is 3 letters and ln is only 2 letters, so it's less writing. And when we get into the next section after January, after Christmas, we start doing a lot of base E stuff. And anytime I do a natural log with a base E for an exponential, it pretty much eliminates it. So, and we'll talk about that as we get going here in chapter 5.7 and 5.8 after Christmas. So just get used to using natural logs, unless they blatantly say you must use common logs, which would be LOGs. Okay, you got to see what it wants. I'm using natural logs. Now, the reason why you want to use the log to both sides is because now I can use the exponent rule. Okay, and if I log one side, make sure you do it to the other side. Okay, so now I bring this x down, and now I've got x times the natural log of 2 equals the natural log of 27. So far, so good. So now the last thing is we need to move this natural log of 2 over, and we can do that using division. This is x times natural log of 2. Just divide both sides by the natural log of 2. And these guys cancel, and I get x equals the natural log of 27 divided by the natural log of 2. Okay, and that's our new way to do it. So that's the new way. So old way, new way. On this question, you could answer it either way. In chapter 5.5, I showed you the change of base formula, especially if you had a T83. We said, well, if I have log of 27 base 2, if I have an 83, I can do the natural log of 27 and divide it by the natural log of 2 and get the same decimal. Okay. You got to see what my math lab wants. They might want an exact value. They might want a decimal, or they might want both. You got to see what they're asking for. So if they want both, I got my exact value, and then I got my decimal, natural log of 27, close it, divided by natural log of 2. Okay, so again, reminder, natural log is next to the 4. Make sure you close that parenthesis on 27, or you're not going to get our decimal 4.755 there. Okay, so the approximation, 4.755. The 8 rounds the 8 up, which rounds the 4 up. And there we go. So final answer, either this one, exact, or approximation. Okay, so let's give that a shot again. Okay, we need to practice this way so that we can answer questions like example 5. Okay, and you'll see what I'm talking about once we get there. All right, so in example 4, a little bit tougher because they have a 4 times 5 to the x equals 17. They have a 4 here. Okay, now don't make this 20 to the x. It doesn't work like that. That breaks all your Dirichlet-Sally rules. So please don't do that. What we can do to get rid of this 4 and isolate the exponential is just divide over the 4. So now we get 5 to the x is equal to 17/4. Okay. Now, my little trick or little visual here is I say this x is up on the high shelf and you can't reach it. Okay, so if you can't reach something, like maybe you got to get some spices from above the cabinet or something, above the microwave, and you got to go and grab those, but you can't reach it. So the next thing you do is you grab something to stand on, and then you bring it down, right? Same idea. The thing I want to stand on is a log, like a piece of wood, right? A big old log. So I'm going to take off a natural log. Now I can reach up and grab this thing and bring it down. So I always say, hey, step on a log so we can bring the x down. Okay, now, if you divide both sides by 4, it keeps it equal. If you natural log this side, you got to do it to this side. You got to keep it equal. So we bring this guy down. We've got x times the natural log of 5, and that equals the natural log of 17/4. And then the last step, divide this natural log of 5 over. Divide it over. Natural log of 5, guys, is some decimal. I don't know what it is. But whatever it is, I'm going to want it over there. So I divide it over. So final answer, I get the natural log of 17/4 and then divided by the natural log of 5. Okay, that's my exact value. That's what I'd punch into my math lab. If they wanted common logs, then I'd do LOGs instead of LNs. Okay. Same thing, if they want the approximation, I throw it in my calculator. I've got the natural log of 17 divided by 4, close it, and then divided by the natural log of 5. And I should get 0.8999. I round to 3 decimal places or whatever it asks me to do. So that's my approximation there. All right, do we have any questions? So we divided over the 4. We stepped on a log to bring our exponent down, and we divided over. If you do it to one side, you got to do it to the other side. Keeps it equal. All right, all right. We got 2 more examples, ladies and gentlemen. Do we have any questions? Am I going too fast? Give me a thumb. Where are we at, guys? Are you following me? Give me a thumb. I got a thumb. I got a thumb. More thumbs. Fantastic. I don't see thumbs down. Nobody has a thumb down. Mr. Gotch, this is easy peasy. Okay. This is like the Army, guys. We can't leave anybody behind here. All right. Why are we learning this new stuff? Well, it's for example 5. Why are we learning logs? Well, if you want to know applications of this stuff, we dive into applications in 5.7 and 5.8. Oh my gosh. Compound interest, continuous interest problems, all right? Making money, growth and decay problems, okay? Maybe you want to be a, what's the word I want? Crime scene investigator. And you need Newton's law of cooling to identify when the person was deceased. Oh man, Newton's law of cooling. Whew. All right, here we go. This is why we learned this new way. If you can see, I've got exponents for both of these sides, right? So I can't just do the change of base. I can't just do exponent equals log with the same base and then the number. I cannot convert this to logarithmic because there's 2 exponents. Which one do I pick? That's crazy. So, well, that x is so high I can't reach it unless I step on a log. Now I can get up on that log and bring this quantity down. I can bring this x down. Now I can start manipulating and solving for x. So I have the quantity 1 minus 2x times the natural log of 3, and then I have x times the natural log of 4. So far, so good. Well, listen to your heart. Your heart's probably telling you what our next step is. I always say listen to your heart. It'll be Valentine's Day before you know it. Your heart's probably telling you I probably need to distribute this thing. So we're going to take natural log of 3 and distribute to both terms. So natural log of 3 times 1 is just natural log of 3. And then natural log of 3 times negative 2x is just negative 2x natural log of 3. And now that's equal to x natural log of 4. Okay. Now, a lot of people get to this point and they start freaking out because of all these logs that are involved. You get all these x's, all these logs. Okay. So what I want you to do is I want you to think of something without logs. All right. So I'm going to remove all these natural logs and you're going to tell me how to solve this thing. So I'm going to cover up that natural log and just write 3. I'm going to cover up this natural log and write negative 2x. I'm going to cover up that natural log, and I'm going to just have x. So if you start freaking out and you don't know what to do, just remove the logs, and this should help you understand what would be the next step in the algebraic process. Well, if I had something like this, 3 minus 2x equals x, the next thing I would do is add this guy over, right? Combine my x's. I would want my x's on the same side so that I could, divide and be done. Right? That's pretty easy. Same idea. We want to get our x's on the same side. Okay? So I want to add this guy over. And what I have now is I got the natural log of 3 equals x natural log of 4 plus 2x natural log of 3. Now I can't combine these two logs. They're different, right? One's a log of 4, one's a log of 3, and it's just, we got numbers in front. You just can't combine them. But what I can do is I look at both terms and I can see that they both have an x, and I can factor that out. So the issue is I can't combine them, but I can factor an x out. So if I take out an x, that leaves me with the natural log of 4 plus 2 natural log of 3. Okay, so get your x's on the same side so that we can factor it out. And now this is just the number. I don't know what this is. It's some decimal. If I typed in the natural log of 4 plus 2 natural log of 3, I know it's a decimal. And now divide that over. This is x times that decimal, divide over this number here. Okay. So final answer I should get natural log of 3, and then all divided by the natural log of 4 plus 2 natural log of 3. So that's my final answer there. Sorry, I ran out of space. So I got x equals natural log of 3, and then divided by natural log of 4 plus 2 natural log of 3. If they want the approximation, you should be able to plug this in your calc. Just make sure you put parentheses around this whole denominator. So I'll show you how to do that in the calc. Okay, so I'm going to do natural log of 3, close that parenthesis, and then divided by natural log of 4. Oop. Let's try that again. Natural log of 3, close that parenthesis, divided by parentheses, natural log of 4, close it, plus 2 natural log of 3, close it, close it. So I have started a parenthesis around that denominator. And you should get this answer. You should get 0.3065. So that is approximately 0.307. Okay. You could also do alpha y equals number 1, like that if you have an 84. So natural log of 3, close it. And then on the bottom would be just natural log of 4 plus 2 natural log of 3. Just make sure you're closing these logs, and you should get the right answer. Okay, if you're not getting that right answer, let me know. Okay, the issue sometimes is people forget the parenthesis there. So if you type this in and you don't have this parenthesis, you're dividing by the natural log of 4, but you're not dividing by 2 natural log of 3. And you get something that's too much. Okay. All right, so, oh my gosh, on the OMG scale, this is like a 7.7, but it's really not that bad. We logged both sides so we could bring our exponents down. They were so high I couldn't reach those x's unless I logged both sides. I step on a log, bring it down. I distribute it over here. Oh, I'm frozen. Try it again. So I distribute it over here. So I got this. I added my x's to both sides so I could factor and divide over. Okay, seems very scary, but this is all stuff that you can handle. Okay, just need a few practices at it. All right, last but not least, I want to do number 6 before we get out of here. This says use your graphing utility to answer this question. Now, the nice thing is we know the answer because we did this exact same question, number 2, and we got 5. So we did this on the front. Okay. So this is really nice. Now we can start solving these things and checking our work with our calculator. Well, to do that, I'm going to use my graphing calculator, my graphing part, and I'm going to make this side y1, and I'm going to make this side y2. Okay, and when I graph those, I'm going to see where they're equal. And to do that, I'm just going to go second trace, number 5, intersect. Okay, but we got to be able to plug in logs into our calculator. Okay, so if I have a TID4 and I want to do log of x plus 3 base 4, I would just do math menu. And I would go all the way down to log base, or go up to go down, and get log base. My base is 4, and then x plus 3 is right there. Plus, if I don't have a calculator, that's a TID4, if I have an 83, then I would have to do my change of base stuff, which I've shown you before. This is the natural log of x minus 3, close it, divided by the natural log of the base, 4. So I've shown you, again, 2 different ways to do this. You can use your log base, or if you have an 83, this is what you'd have to type in for both of those. And then y2 is 2. Okay, so this is going to be a log This is going to be a horizontal line. So I'm going to go ahead and graph these now. Let me know if I'm going too fast. When I graph the blue one, there's y1 and here's y2 cutting across. And I want to find out where these guys are equal, where they're equals right about there, where those two graphs intersect. So I go second trace, intersect. So number 5, press enter. Right or first curve, I got to find it first, so it's after 3. So move my right cursor towards the right until I can see it on the blue one. Press enter. Second curve, press enter. Guess, press enter, and it jumps to my intersection, and I got 5, 0. So x equals 5 is my solution. Okay, and that's what we got before. As you can see, there is nothing over here at -5 because that isn't part of the domain. Okay, there is no negative values that I can plug in. Okay. All right, ladies and gentlemen, do we have any questions on 5 or 6? Any questions on 5 or 6?